What are vertical curves? Vertical curves are the second of the two important transition elements in geometric design for highways, the first being horizontal curves. A vertical curve provides a transition between two sloped roadways, allowing a vehicle to negotiate the elevation rate change at a gradual rate rather than a sharp cut. The design of the curve is independent on the intended design speed for the roadway, as well as other factors including drainage, slope, acceptable rate of change, and friction. Those curves are parabolic and are designed stationing based on the horizontal axis. The curve provides a gradual change for haulages from one inclination to another. The curve leading to the top or brow of an inclined plane would be the convex, and at the bottom would be the concave. So these are the two types of vertical curves. The first is the summit curve, and the second is the valley or the sag curve. So for the summit curve, Summit curve are used when the change in grade is negative. So in other words, when two grades meet at the summit and the curve will have convexity upwards. For the valley or the sag curve, they are used where the change in grade is positive. In other words, when two grades meet at the curve, it will appear downwards.
So our next topic would be symmetrical curves. Simply put, it is a curve having equal lengths on either side when cut in the middle. As you can see, here is a curve and here is line PVC and PVT. And PVC is connected via curve to PVT. When you cut it in the middle, as you can see here in the slide, side A is equals to the total length divided by 2 and side B is equals to the total length divided by 2. So if the total length is 6, side A will be equal to 3 and side B will be equal to 3. Applications and uses for symmetrical curves is on road construction to allow the change of the slopes of the road. This used to provide gradual change between adjacent vertical grade lines, and the curve used to connect the two adjacent grades is a parabola, as you have seen in the previous slide. So we have here a curve. PVC stands for the point of vertical curve and PVT stands for the point of vertical tangency. PVC extends upwards, so it is denoted G1 positive or gradient 1 positive, while PVT is G2 negative since it is going down obviously, so it would be gradient 2 or G2. And the point where PVC and PVT meet is of course the point of vertical intersection. So these are just some of the terms that we must discuss when we talk about symmetrical curves. Moving on, here is a much detailed picture. So we can see that side A is equals to L over 2 and side B is equals to L over 2, and G1 is upwards, G2 is of course downwards, and the distance between the point of the curve to the point of vertical intersection or PVI is denoted as the height. So now we will be deriving some formulas of symmetrical curves. For this slide, I want you guys to focus on the one I encircled in red. So if you extend PVC upwards, or if you extend it to the same direction it started, and if you extend PVT vertically, you would actually form a triangle as seen in the one I encircled red. So now I want you to focus on the formulas on the upper left. So you can see that you can form two right triangles. And in order to get the angle theta of the right triangles, of course, you must use the tangent, since it is opposite adjacent, or rise over run. Tan theta therefore would equal to 1 over x, and since it is gradient, so I multiply it by 100. So tan theta equals 100 over x. And since it is percentage, so it is therefore just equal to gradient. So tan theta is just equal to gradient in this scenario. This is where it gets a little confusing, but let me explain it more. We now know that tan theta is equals to g. So therefore, we focus our attention on the formula, or on the solution I encircled with the yellow marker. So tan theta is equals to g1, which is evidently equal to a over L over 2. So what is a? A is just the opposite side of theta, as you can see in the drawing. So a is actually a variable, and it can vary. So it can be a, b, c, or x. So but for this, we'll just use a. And it is divided by L over 2. So as you can see, the one I encircled purple, that is actually L over 2, or just the adjacent side of the angle theta. So L over 2 is just actually one of the sides of the horizontal line. Therefore, to get x, or to get the opposite side, or to get a, you must therefore multiply g1 by L over 2. Hence, if you can see at the one I encircled red, the opposite side is equal to g1 over L, g1 multiplied by L over 2. And since below it is also just a right triangle, it is just g2 multiplied by L over 2. So the entire side would be equal to L over 2 multiplied by g1 plus g2. Moving on, we now find a formula or an equation to find h, the one I encircled red, as you can see here. So it is the distance between the curve to the point of vertical intersection, or the vertex. So here is another picture. So this is just a similar drawing from the previous slide. This is actually the same drawing from the previous slide. So h is encircled, h or height is encircled in yellow. And you can see that we can actually form a bigger triangle, a bigger right triangle, as you can see in the marker red. So we now know that the opposite side is L over 2 multiplied by g1 plus g2. And the adjacent side is just the total length. So in order to get the height, we establish certain parameters. So as I've mentioned earlier, L over 2 is multiplied by g1 plus g2 is the opposite side, and the total length is the adjacent side, and 1/2 of that adjacent side is L over 2, since it is just one side and it is a symmetrical curve. So it should be equal to L over 2, one side. On one side. So in order to get the height, we simply use the ratio of proportion. So we get 2h divided by L over 2, since equals to the L over 2 multiplied by g1 plus g2, or the opposite side, over L. We get, therefore, we then isolate h to get 2h equals the L over 2 squared multiplied by g1 plus g2 over total length, and then we get h equals L over 8 multiplied by g1 plus g2. So here is our final formula to get the height. So after this, we then move on to some examples and real-world applications of symmetrical curves.
So for a sample problem for symmetrical curve, so a grade line AB having a slope positive 5% intersects another grade line BC having a slope of negative 3% at B. The elevation of points A, B, and C are 95 meters, 100 meters, and 97 meters respectively. Determine the elevation of the summit of the 100 meters parabolic vertical curves to connect the grade lines. As you look at the diagram, the elevation of point A is equals to 95 meters. The elevation of point B is 100 meters and the elevation of point C is 97 meters. So the horizontal distance between A and B is equals to 100 meters minus 95 meters over the slope, which is 0.05 is equals to 100 meters. So on horizontal distance between B and C, so is equals to 100 meters minus 97 meters over the slope, which is 3% or the 0.03, which equates to 100 meters. To determine the elevation of the summit of the 100 meter parabolic vertical curve to connect the grade line, we will get first the S1. Since the grade slope is directly proportional to the distance, the grade at A at PC is 5% and the grade at PT is 3%. Then the grade of the summit is 0. The grade varies directly with the distance, so meaning there is a straight line or linearly as what shown in the grade diagram. So with that, we can easily locate of the summit. We can call it S1 and we can solve that using ratio and proportion of the similar triangles. So S1 over 0.05 is equals to the width of the point C, PC, and PT, which is 100 meters, over the sum of each grade, which is 0.05 plus 0.03. So then move the 0.005 to the right to get the S1. So S1 is equals to 100 meters times the 0.05 over the 0.08. So S1 is equals to 62.5 meters. Next, to get the elevation of the summit, we need to know the height because it will be the elevation of the PC plus the vertical distance. But we don't have the elevation of PC, so we need to get the elevation of PC. To solve the elevation of PC, we need to have the height or the H1, which is the vertical distance between PC and the highest point of the summit curve, which is 50 meters times the slope, which is 5%. So 50 meters times 0.05 is equals to 2.5 meters. Then add it to the elevation A, which is 95 meters. So the elevation PC is 97.5 meters. Then, to get the elevation of the summit, we must add the elevation of PC and the YD, which is the elevation of PC is equals to 97.5 and the YD is unknown. To solve for YD, we will get the area of this triangle, which is 1/2 base times height. So 1/2 times 62.5 meters times 0.05, which is equal to 1.5625 meters. So knowing on the value of YD, then we can solve the elevation of the summit. So 97.5 meters plus 1.5625 meters equate to, so that is 99.0625 meters. So the elevation of the summit is equals to 99.0625 meters.
Hi everyone, I am Lagumbay Masao, and I'm going to report the unsymmetrical curves. So what is unsymmetrical curves? An unsymmetrical vertical curve is one in which the horizontal distance between the PVI and the PVC is greater than the horizontal distance between the PVI and the PVT. To put it another way, L1 does not equal to L2. And unsymmetrical curves are commonly referred to as doglegs because they have an even tangent. An unsymmetrical curve is distinguished by two uneven tangents, which result in an unequal partition of the curve at the VPI. The slope of the two parts of the curve under the two tangents vary at different rates, and at the point beneath the VPI represent the transition between the two speeds. So when can we use the unsymmetrical curves? Unsymmetrical curves may be justified in circumstances with constrained geometrics such as highways with several control points, freeway ramps, and grade-separated construction that need a minimum vertical clearance between two roads. This is the formula for unsymmetrical curve, and these are the steps. In the figure on the right side, let's imagine there's a bridge structure standing on the unsymmetrical curve. First, we need to determine the minimum, middle, and the max clearance. You always start at the minimum clearance. First, you need to get the x with the formula of x sub 1 equals L sub 2 minus open mid-station at PVI minus mid-station at PVT close parenthesis. Before getting the y sub 1, you need to get the height first, and these are the formula of height. H equals L sub 1, L sub 2, open, G sub 1 plus G sub 2, close parenthesis, over 2, open, L sub 1 plus L sub 2, close parenthesis. And for the y sub 1, or get the y equals x squared times h over L sub 2. Lastly, in getting the minimum clearance of the structure that is built in the unsymmetrical curve, you need to solve for the clearance. And the formula of the clearance is minimum clearance equals open elevation of underside minus PVI elevation close parenthesis minus A minus Y. And that's all for getting the formula for an unsymmetrical curve.
For sample problem for unsymmetrical curves, we already have a diagram and a given. So we need to do is to find the elevation of the curve, the underpass. So the givens are the G1 is equal to 7%, the L1 is the 160 meters, the G2 is negative 4%, and L2 is 120 meters. The elevation to the peak is equals to 30 meters and its height is 4.42 meters. So first we need to get the y, but before that we will determine first the h to get the y. So we will use the formula h is equals to g1 minus g2 times l2 times l1 over 2 times L1 plus L2. So substitute H is equals to 0.7, which is the G1 minus negative 0.04 times 120 times 160 meters over 2 times 160 meters plus 120 meters. So the value of H is equals to 3.77 meters. Then, using the squared property of parabola, we can get now the value of y since we have already a value of h. So the formula is y over x squared is equals to h over L2 squared, which is x is equivalent to L2 over 2. Then transfer x squared to the right to make the formula to y is equals to h times x squared over L2 squared to solve the y. So substitute. So y is equals to 3.77 meters times 60 squared over 120 squared, which is equal to 0.94. Then we can now solve the value of elevation of the curve, which is elevation of the curve is equals to elevation v minus L2 over 2 times G2 minus y minus h. So substitute. Elevation of the curve is equals to 30 meters minus 60 meters times 0.04 minus the value of y 0.94 minus the height, which is 4.42 meters. So the elevation of the curve is equals to 22.24 meters.
Passing distance. Passing distance is the distance that drivers must be able to see along the road ahead to safely and efficiently initiate and complete passing maneuvers. While passing is not an event that is a major factor in the design of 4-lane highways, it is a critical component of 2-lane highway design. The capacity of a 2-lane roadway is greatly increased if a large percentage of the roadway's length can be used for passing. On the other hand, providing a sufficient passing sight distance over large portions of the roadway can be very expensive. Simply put, the passing sight distance is the length of roadway that the driver of the passing vehicle must be able to see initially in order to make a passing maneuver safely. So these are the 6 assumptions that incorporate vehicles. First, the vehicle being passed travels at a constant speed throughout the passing maneuver. The passing vehicle allows a slow vehicle into the passing section. Third, upon entering the passing section, the passing vehicle requires some time to perceive that the opposing lane is clear and to begin accelerating. Fourth, while in the left lane, the passing vehicle travels at an average speed that is 10 miles per hour faster than the vehicle being passed. Fifth, an opposing vehicle is coming toward the passing vehicle. And lastly, there is an adequate clearance distance between the passing vehicle and the opposing vehicle when the vehicle returns to the right lane. So this is a sample problem. Calculate the passing sight distance by hand and then compare it to the values recommended by AASHTO. In your calculations, assume that the following variables have the values given. So passing vehicles driver's perception or reaction time is 2.5 seconds. Passing vehicle's acceleration is 1.47 miles per hour per second. Initial speed of passing vehicle is 50 miles per hour. Passing speed of passing vehicle 60 miles per hour. And so on. So first is we need to calculate the passing sight distance of D1. So we use the formula D equals VT, where V is equal to 73.3 seconds and the time is 2.5 seconds. So the distance traveled during the acceleration portion of D1 is computed using the equation VF2 is equal to VI2 plus 2AD, where VF is equal to 88 feet per second and VI is 73.3 seconds. So next is A is equal to 2.155 feet per second, so that's equal to 1.47 mph per second. So we need to solve for D, which yields a value of 550.1 feet. So the total distance D1 is equal to 733.4 feet. So the second portion of the passing side distance is the distance of D2, which is defined as the distance that the passing vehicle travels while in the left lane. So the time it takes the passing vehicle to traverse these distances relative to the slow vehicle can be computed from the equation, again, D equals Vt, where D is equal to 84 feet times 20 feet plus 22 feet plus 22 feet plus 20 feet. And V has a value of 14.67 feet per second. So the total passing side distance is D1 plus D2 plus D3 plus D4, and we get 1,811